be very important for future design. And recently we have the cross megawatt ammonia co-firing system built in Beijing, in Tsinghua, collaborated with the industry. This, I think, in the future can be a very good very good pilot skill test for the ammonia co-combustion. That's will also test for some of the pilot skill burners. That's a summary. I don't repeat the summary. I think for the ammonia co-combustion with the methane and ammonia co-combustion with the coal, and so I think the equilibrium ratio, like the fuel rich, the condition is very important, and the how to splitting the fuels and the air splitting to organize, that will be very important. But how to link the laboratory research with the industry skill research, that's much important. Thanks. And also, finally, I will acknowledge for the colleagues, Professor Qiang Yao, and my colleague, Professor Jiankun Zhuo, and Tong Si, and Yuan Ping. Also, for my international collaborators like Neil Hasi, and also the Oswaldo and Professor Bai. Thanks.
Thanks for Professor Li. Please ask the question. Okay.
Nice presentation. Just have one question for what's the velocity that you have for this burner when you have the natural gas burner? What's the velocity?
Velocity in our burner? It depends. Sometimes we can be from the about 5 or some 5 to 10 about this.
Okay. Are you looking also into do more variations because of your stability map? You will be quite affected with the burner.
Yeah, that's a good question. But your question is very good. But we use some idea similarity. We just to control the reaction time and also the flow times. These 2 times scale. Even indeed in your laboratory burner, you use the velocity in the bigger one, but sometimes maybe it's not. It's not good for your laboratory burner. It depends. You should the time scale analysis or something. Yeah, good.
Okay, thanks.
Good suggestion. Yeah, okay.
Any other questions?
Hendrik Nicolai, TU Darmstadt, thank you very much for the comprehensive overview. Maybe I have more a general question. So you talked a lot about experimental scale up. In terms of modeling, do you see any potential bottlenecks at the moment for ammonia coal combustion? So I think in the last years we worked a lot on modeling pure coal combustion. Do you think that we need to improve now for also ammonia coal combustion?
Yeah, so what's the point of the future, the ammonia coal combustion? What's the main point?
Yes, the question is just kinetics important, or do you think we need other CFD models to better predict the process?
If you involve the co-combustion, sometimes the kinetic models it will be quite important. But different to gas, we must like Sandia, like they have do some of the kinetic model, but that kinetic model is, I think, most important is the pyrolysis model. We can verify that with the like a laboratory experiment, and then pyrolysis for the gas kinetics, we can use some of the model from the gas combustion, and how to combine these two. Well, it's very important. Yeah, for in our collaboration with Professor Hasi, like Peng Ma, have do some, but because the co-combustion is a very large scale, we still want to use not much, quite the key, not so parameters. It's very the small the parameters and to adjust the model, and then can use it for the CFD. Okay, good
Thank you
suggestion.
very much.
Thanks. Okay. Okay, please. Please.
Professor Lee, I want to know why do people often use the critical as NH2, not the NH2 characterize the combustion of the ammonia during the co-combustion? And is it important to use the NH to characterize the combustion?
Yeah, it's too like is for for such for in our research my group we are not the laser diagnostic group. We want still to use the technology. We use the camera, the CCD to get the signals very easily, very quickly, and also for such kind of technology, the filtration for is because for the scattering from coal from arcing very important. So here we will consider this to H2 it's just for gas flame, for coal flames. In our case, there will be much easier to, and the signals is enough, and also it's at the point of the reaction pathway of the ammonia decompression. It can characterize the ammonia decompression. That's we consider this. It's just we globally consider all the effects and select it. Okay.
Okay, thank you.
Thank you.
Now I have 4 minutes. Please ask another question.
Professor, thank you for your very interesting presentation. I was particularly pleased to see your particle emissions results towards the end.
For PM,
yeah. Do you have any sense of whether the co-combustion with ammonia affects the composition of the particles?
Right.
Because the size is there, but just have you done anything on the composition as well?
That's a very great question. So for the PM, this part is not important. It can be captured by the ESP, electrostatic precipitator. But this part is not only for the very toxic emission, and also it's also very important for the slugging, because the small particles can adhere to the steam tube, and then dramatically. So with ammonia, we will care about. Recently, we have very good model. Previously without ammonia micro, we have very good prediction model with the problem balance, and also verify with our test, and we can to know the PM, the submicron PM like formation, and with ammonia, there will be increase the combustion for the first stage like volatile. At this time, even the small particles, their change is not linear. It's very complicated. So the ammonia, maybe ammonia, the ratio is 10% increase, maybe 50% because less coal. So that will be we focus this part.
Perfect. Thank you so much.
For this burner, I think this burner is the best the equipment for study. If we use a very small flat flame burner, it's not enough, because it's not a self-sustained flame, co-flames. Yeah. Okay. Good question. Yeah.
Thanks, Professor Lee. Let's co-chair Flex and I confer the conference certification for Professor Lee. Okay, there's 5 minutes past. So the second the second lecture is the invited lecture, strategy for ensured flame stability and controlling nitrogen oxidase for pure ammonia combustor. Let's welcome the Min Juni professor from Korea.
To introduce me, so yeah. Can I use the? No, please. There. My name is Min Jung Lee. I'm from Seoul National University of Science Technology, and today I talk about the strategy for ensuring flame stability and controlling nitrogen oxide in pure ammonia combustor. So here's our contents. So briefly introduce some backgrounds, and then I show you some pure ammonia combustor, and R&D some activities in Korea will be followed. So now we are living in some carbon-free fuel era. So including the both hydrogen and ammonia, just we use this one, wanted to use this one it should be generated from renewable energy, and then also it can be export this renewable energy to overseas, and so it is called to energy carrier. So recently in South Korea also proposed the enhanced NDC target. So we have a lot of carbon dioxide should be decreased like this. So we also need a large amount of hydrogen. So we also consider about the hydrogen carrier effective way to import the hydrogen from overseas. So ammonia is, as you know, is most economical means for importing from hydrogen from overseas, like this. So anyway, we also consider about the many different way to, or different pathway to import the hydrogen. So can you give me some? Yes, there is some competition among the liquid hydrogen and then ammonia itself and ROHC at the same time. So, but the most cost-effective hydrogen transport pathway can be determined by the size and distance. So we have to import from Australia and the Middle East, so it is far from over 7,000 kilometers. So ammonia is most effective way to import the hydrogen, like the Japan side. So as you know, so the global ammonia demand should be increased like this for the agriculture. There is some conventional applications with because of the increase of populations, and then some new applications should be added like this one. So actually, in South Korea is placed at the first locations like this one. So we imported a large amount of ammonia and 1.1 million tons per year. So we have a lot of infrastructure. So we are very, we have very large amount of infrastructure. So we are, so we want to extend the ammonia markets, and then some ammonia related industry. So we also, in the power sector, we just use this ammonia as a fuel like this one. So the government reported the percentage of the ammonia in the power sector, and then we need about 3 million tons in up to 2030. It is comparable to Japanese size. So actually, this is a very large amount of ammonia. So we also need the hydrogen carrier, like we need also a lot of hydrogen So about 50% will be imported from this total amount of hydrogen. So the clean ammonia value chain can be summarized like this picture. So in terms of the carbon-free combustion, the end use. So the large amount of the carbon-free ammonia should be imported from overseas, and then we can use the ammonia and then hydrogen, and between this one, so we just we can use our cracking gas. The cracking gas means including the hydrogen and nitrogen with very little amount of ammonia. So if you decrease the NOx emissions, we have to eliminate this little amount of ammonia should be eliminated by absorbing any other techniques. So this is our global this is clean ammonia value chains, and then I show you some brief my overview of the ammonia combustion related technology for application areas. So it can be the primary, finally, the primary fuel can be determined by the systemic, the complexity or the phase of primary fuel. So in this, we are now living in the present state, like there is some variation in terms of the status of development. So after that, so finally we can get some primary fuel like that status. So I briefly introduce now some my techniques for about the pure ammonia combustion. So the first study of ammonia flame can be found in the 19th Journal of Nature. So it is earlier than the Haber-Bosch processor. So at that time, so he found that don't know him. So but in the context, so you can find the very interesting phenomena. So just he found the yellow color flame, and then he also checked the considerable NOx emissions, and then also he recognized that the ammonia flame is very difficult to burn like this. So we are also still consider about these two parameters, 2 and 3. So over the 100 years. So just I want to show you how difficult to stabilize the ammonia flame. So this video was captured last Saturday for this presentation. So as you know, so we just use this when we use simple nozzle jet is diffusion flame. So when I use the methane flame, so we can generate the very stable flame easily, like this one. So, but if you increase the more specific volume flow ratio to the ammonia, the stability was changed to very poor. So, and then finally, if you change it more than 100 ammonia, so there is no stability flame. You can get maybe many researchers are already know that about this phenomena, but the other researchers didn't know how to difficult this flame stabilize like this phenomena. So if you use the premixed flame, the phenomena is very similar to the diffusion flame. Like we cannot acquire the stable flame like the pure ammonia combustion status. It is the equivalence ratio around 1. So, and the third one is pilot burners. This is commercially used. I just bought the pilot burners. So it is very stable flames to when we use just the methane flame. So if you increase like increase the ammonia, so the flame colors changes like okay. Yeah, and first one the methane only, and then we increase the ammonia, so color was changed like this one. Over the 80%, it is still remains. So it's much more good, better than any other burners because there is some solar inside there. So, but if you increase more than about the 100%, so flame cannot exist itself. So just I consider about ammonia like other fuels. So it requires a burner, capable of stable combustion without the assistance of any other fuels like oxygen enhancing and heating and plasma. So just because we want to use ammonia as a primary fuel as a near future, so it should be changed or require the very ammonia related burners. So we succeeded in develop this burner, so tangential injection like tangential injection burner. So at the same conditions, we can get the very flame inside the tube like this one. And this is just a simple, simple geometry. It is tangential injection combustor. It's just two inlet port like this one, very relatively high velocity. So the solar number, geometrical solar number is over 3. Like it is much larger than the conventional solar number like this one. So due to this high solar number, so there is the negative axial velocity regions exists. So actually, like this one, or in the middle picture of this one, so you can find this flame is not self-propagated flame. So flame was induced by the recirculation zones. Flame pushed toward the upstream like this one. So this is very simple but I think very important phenomena. So we just tested about the increase the net velocity and then different equivalence ratio like this one. So, yeah, and then also some comparison of stabilizing region, and then you can find the very different phenomena when you push toward the near lean blowout limit and the Ricci blowout limit like this one. The flame in case of lean blowout limits, so flame was shrinked like this one, and then Ricci blowout limits, so flame has lifted at like this one. So we have to analyze this phenomena like for the very various velocity regions. And then using this tangential injection combustor, so we applied the many configuration like this one in terms of combustion load like this one. So we increase every year, so about 10 times or 1 orders like this one. So we now tested about 100 kilowatt like this one, and then next year we increased more than 10 times larger than this one. So it is various proposal like this one. So just in to the ammonia cracking burners, so especially the fuel type is more complex than any other things. So in just I focus on this gas turbine combustor like this. So and then I show you some the NOx emission aspects. So we already know about the staging combustion. So most of researchers are familiar with the air staging combustion. So this is calculation. So I explain some difference between the fuel staging and the air staging. So in the air staging, there is and after the first stage, like there is a little amount of NOx emissions because the Ricci conditions. But if you introduce some secondary air, so the NOx emissions should be increased like this one. And then the fuel staging is opposite. Yeah, because the fuel staging is more operated. The first stage is more lean, so large amount of NOx emission is already emitted. But if you use the ammonia as a NOx reductant, so the NOx emissions should be reduction by this way. So I just compare this staging techniques. So but and I also compare the temperature with variation of temperature. So as you know, so air staging is a very efficient way to reduce the NOx emission in terms of combustion outlet temperature. But in specific regions, fuel staging is much higher effective to other than the air staging. So this specific region is already you know about this window. So it is called essential temperature window. So, but I want to highlight this one. So, just we think about the essential in higher pressure conditions. This is related to combustion, gas turbine combustion. If you increase more pressures, the operated combustion highly pressurized combustion. So just we experimented these two staging techniques. So firstly, I tried to axial types like any other studies, but I want to decrease the combustor length. So I adapted the coaxial fuel staging like this one. So and then I tested the high pressure environment like using this combustion chamber. And this work was done the last year. And at that time, so I picked. Which one? Yeah, you can find a very stable flame inside the tube and then combustion chamber like this one. This is just only pure ammonia, air. And then this year, so I moved to our university. So this work performed by Dr. Kwak and the current PI in this project. So he also increased more pressure and up to 10 bar, and they introduced some percent of ammonia, small amount of ammonia in the coaxial flow region. So you can find a very effective result. So NOx can be reduced from the 100 ppm to lower than 40 ppm like this one. So, and then there is a little amount of ammonia slip. You can find that. So it is a very effective way to reduce another way to reduce the ammonia related NOx emissions. Yeah, so and I show you some activities in recent activities in Korea. So I briefly just one pages. So the ongoing project title is development of core technology for ammonia-fueled gas turbine combustor for power generation. So it just started about 2 months ago, and the budget was 8.3 million, and I'm in charge of developing some pilot nozzle for a cold start. So I just use ammonia. So I don't use I don't want any other fuels and plasma and then other things. Just to start up, so I developed this tangential injection burner as a pilot nodules, and some other research institutes also related this work, and especially all 5 representative power company in Korea also participated in this project as a demand company like this one. So we will touch the nozzle and then also combustor and the high pressure testing environment, and then I also want to some reliability related work. So it is maybe thermal coating and the material evaluation like this one. And then so we also consider about the liquid ammonia combustion. So maybe somewhat diverse and research are included, but Korea also just I want to say you, so Korea also begin the gas turbine combustor development like this one. Yeah. Okay, here's my conclusion. So the stability of pure ammonia flame can be achieved through a high Swirl number. It is a very simple phenomena. So you can generate the negative velocity regions. The flame can push towards the upstreams like previously shown. So to suppress the NOx emissions for the ammonia flame, so air staging is very good scheme for reducing NOx emission, but you can add it the fuel staging technology at the same time. So this can be applied depending on the operating temperature and then pressure. And the securing the cold start and technology is crucial for ammonia to serve as a primary fuel near future. Yes, thank you very much.
Okay. Thanks, Professor Minju Li. Please ask question. Now we have only 3 minutes, so I will ask the 1 or 2 question.
Thanks for the very informative talk, and also I thank the previous one, Professor Li. You both mentioned this air stage and the field stage, but I'm sorry, I found the NO emission still higher than 200 ppm from your study and from his study. Can you comment in the future? Can we use some more advanced technology to decrease this level to like 100 ppm?
Yes, actually this is our result at the 10 bar. So the NOx emission was lower than 40 ppm. It is corrected.
How about this overall equivalence ratio?
Overall equivalence ratio is lower than 1. So there is a 4%, 2 or 4%. Lower than 1. So this is high pressure environmental region. So we didn't report it at all. Yeah. Okay. This is
yes,
experimental.
high pressure is good for the depletion of NO
Right,
mix.
yeah.
And how about this
Essential.
temperature? When you increase the pressure, you also the temperature you keep it low or also increase the temperature?
Yeah, this is the fundamental study. So because there is a larger window, so the larger amount of heat is the losses through the environment. So you can find the real value of N2O emissions. It is come from this heat losses. So after that, and then we enclose the all side, and then we increase temperature and then pressure at the same time. We will evaluate it. That, yeah.
Okay.
Yeah. Thank you.
hosted by Professor Felix Nietzsche. For all the conference postponed for 5 minutes. Okay.
So, yeah, thank you, Professor Jiao. Next, we have a speech from Shiqi Wang and Chuntong Chong on revealing NO formation kinetics.
welcome to the second part of the morning session. So this part is about plasma synthesis. And our first speaker is a keynote speaker, Professor Xianhu from University of Liverpool. He is working in the Department of Electrical Engineering and Electronics. His research mainly focuses on plasma chemistry and plasma catalysis for environmental cleanup and the sustainable production of fuels and chemicals, including gas cleaning, methane activation, carbon dioxide conversion, hydrogen production, nitrogen fixation, and so on. He has published over 200 papers, and he got a lot of awards. The title of his talk is Plasma Electrification for Decentralized Production of Green Ammonia. Welcome, Professor Xianhu.
Okay. Yeah, thank you very much for the introduction. Also, I'd like to thank the organizer to give me this opportunity to share works on plasma chemistry and plasma catalysis for ammonia production. So I'm from Liverpool. So this is a brief introduction about the outline of my presentation. So including introduction, and also I talk about the plasma catalysis for ammonia synthesis from nitrogen and hydrogen route. But then I will talk about tandem plasma electric catalysis for nitrogen fixation. Then a brief summary. So our society actually is currently, facing global challenges, mainly, global warming, climate change. For example, we have experienced like extreme weather. So CO2 emission, continue to rise. So decarbonization of all sectors is critical to achieve net zero. One actually promising strategy actually is electrification. So which can actually, speed up decarbonization process. So especially, for example, for chemical process or chemical industry, that currently, the most chemical process, they largely rely on fossil fuels. So actually need a, decarbonization. So actually we need action now. So for example, especially developing like emerging, new technologies to address the challenges. So plasma actually, fit to this scenario, quite well. So plasma actually the full state of matter. So it's different to, solid, liquid, and gas. So plasma actually contains a mixture of electrons and also reactive species, including, radicals, excited species, to initiate chemical reactions under mild conditions. So here I just want to focus on no thermal plasma, which actually has low temperatures. So the main advantage of no thermal plasma actually, for example, chemical reactions, which can, can be proceeded, under mild conditions like low temperatures or room temperature, ambient pressure, to avoid, high pressure, high temperatures typically required, in thermal process. This actually is very important for, decentralized production using renewable energy. And the one, very significant, unique advantage actually is plasma process can be, instant switch on off, this actually offers great flexibility to be combined with renewable energy, especially intermittent renewable energy for, decentralized production of fuels, chemicals. And also the process can be modular and scalable. Overall, this can offer, flexible electrification, for, decentralized, modular, and on-demand production using intermittent renewable energy. So here, two, typical, no thermal plasma. So one is DBD, dielectric battery charge. The other one is, gliding arc, which can be used for cracking, and the DBD is more suitable to combine with the catalyst for, a range of chemical reaction, for example, ammonia synthesis. So in many cases, we actually want to combine plasma with catalysis because for many reactions, we know that the plasma is really, highly reactive because you have electrons, reactive species, but actually we need, but typically have poor selectivity. And the catalyst, we know that you normally can design the catalyst which can, control the selectivity, but also have activation barriers, both, either, thermodynamic or, kinetic, barriers. But so if we can combine plasma with the catalyst, we have the potential actually to generate a synergistic effect which can enhance, the conversion, selectivity, and energy efficiency. But if we look at, the reactions, for plasma, it's mostly, gas phase reactions. But for catalysis, that's mostly, surface reactions. But plasma catalysis actually involves both, gas phase and the surface reaction. So it's more complicated, than either of them. In terms of this kind of system, you will see that this actually is multidisciplinary subject. So if you design a system like this, you need to consider how you can design the plasma reactor, because this affects the plasma properties and also chemical reactions. But also you need to consider how you design the catalyst, which can be used for plasma catalysis. But also you need to consider plasma catalyst interactions. So I will give some examples in my talk. There are two typical, configurations for plasma catalysis. One is we call the single-stage plasma catalysis. You put catalyst in the plasma reactor. So all the species generated by the plasma can interact with, the cat surface. So this is used very common because we can do the reactions on the moderate conditions when we use this kind of configurations. The other one is, the two-stage plasma catalysis, or we can put catalyst, after plasma or before plasma, but it's most often, you put catalyst after plasma reactions. So this is more like, plasma reaction with a catalyst reaction. So this is typically called a two-stage plasma catalysis, but also you can expand this one to, for example, the plasma with like electrocatalysis or photocatalysis, it's called a tandem, plasma catalysis. So this is typically used, for example, for VOC oxidation, and you also want to remove ozone, after plasma reaction, or you can use this kind of, the plasma is like a microwave plasma. You can use the, the heater to actually heat the catalyst bed. So plasma catalysis actually, in terms of mechanism, is more complicated because you involve gas phase reactions and also surface reactions. So you also have a gas-solid interface. In addition to like the conventional LH mechanisms, on catalyst surface, plasma catalysis, you also have very important pathways is, through the ER route. So any radicals, the reactive species in the gas phase can also interact with the surface, on the surface. So this create, additional pathways for, the plasma catalysis. But also, in some cases, you can also find for example, plasma can create oxygen vacuums, defects, which can also help to, for catalyst properties. And also probably you can also enhance, electric field. So here we actually, a few years ago, we actually, we deliver one, the roadmap, and we actually list some reaction using plasma catalysis. You can see mostly, it's, like C1 molecules, like CH4, CO2 conversion, but also have nitrogen synthesis, ammonia synthesis, and NOx synthesis, but also like VOC, odor control. On the other hand, if you look at the right one, this is something expanded from plasma catalysis. You can use the plasma for the treatment modification of surface, the catalyst. So this can be used, for example, for, initially, I think, many years ago, the people, use plasma to create, like a coke-resistant catalyst for thermal catalysis. But nowadays, there's also some, groups using plasma actually for the treatment of electrocatalyst or photocatalyst to create, like defects, oxygen vacuums. In terms, large scale, development, there's also some examples. For example, one is ozone generator, which has, has already been commercialized, for example, like Toshiba, Siemens. And the largest scale currently, in Montreal is 45 megawatt. So this is used like, in parallel. And also, there's also some, a gas cleaning process from denox, desox using pulsed plasma. So this is like 1 megawatt pulsed plasma. And to deal with 250,000 cubic meter per hour flue gas, developed by, teams in China. So they actually have built 5 plants for, this kind of system. So next I will talk about, ammonia. So we know that, I think, you probably know that this, the Haber-Bosch process actually is currently, dominant process for ammonia production, but this is typically, centralized, large-scale plant. And actually, the concern at the moment, to achieve net zero, actually, the harsh operating conditions like high pressure, high temperatures, and also this actually the process consumes 2% of global energy. It's mostly from the steam from natural gas, so and also emit like CO2. So you know that actually during the war between like Russia and the Ukrainians, actually the natural gas price increased and the hydrogen price also increased and the fertilizer price increased. So the BASF also, closed down the ammonia plant actually in Europe. There's another problem for this kind of process. If you want to decarbonize, like Haber-Bosch process, you'll probably see the gap between, the large scale, this ammonia plant, which like decentralized or, small scale, the wind or solar. So this is also another issue. So at the moment, there's a lot of interest, to look at, how we can develop, produce ammonia in a sustainable way. So, how we can produce, ammonia under mild conditions. So here, this is a review paper from Jing Guangcheng, from Columbia Universities. They also talk about the nitrogen cycle, and also mentioned some like emerging, process, for example, plasma and electrocatalysis to address the challenges in ammonia production. So if we look at the history of ammonia production, the plasma actually, it actually was in 1903. It's a process called the BE process. It's two actually researchers from Norway. They actually developed like an electrical arc process to produce, NOx, which actually the way to actually fix, for nitrogen fixation. So you actually can, oxidize nitrogen to NO, then, to NO2, then you put into water, you get nitric acid. So this is initially developed by the plasma process, but it's overtaken by, the Hart-Bosch actually in 1927 because of the energy cost. So I mentioned here, this for the BE process, the energy cost for, NOx production is about like 2.4 megajoule per mole, but Hart-Bosch actually is around like 0.506 megajoule per mole, okay? But this actually the process, has come back again at the moment because we can use renewable energy. So I will talk about this one later. So this is at that time is the two researchers. One is Birkeland, the other one is Ada. They actually use electric arc to produce NOx, NO and NO2, and then to produce like nitric acid. And this is the one actually the reactors, plasma reactors actually currently in Norway in a park actually. And this is the previous, the power stations actually, they use hydroelectrical to, the power this kind of process. And they have like 35, the reactors in parallels, and each one has like 3,000 kilowatt. So currently there's a lot of interest, in plasma technology for ammonia synthesis or, nitrogen fixation. The one actually, the reason is also, if we look at this one, is from a review papers, and you can see that the Hart-Bosch process is almost close to the theoretical limit in terms of energy cost. But plasma process actually, it's the cost actually, spans a wide range. But in terms of theoretical limit, actually, it's much lower than, the conventional Hart-Bosch process. This actually, is need to be achieved actually using, for example, vibration excitation, or probably need like a low pressure. But I think for plasma process, it's not necessary you need to achieve the, the low energy cost, compared to like Hart-Bosch, because actually plasma process can actually reduce, capital cost significantly. So I will first talk about the ammonia synthesis using nitrogen hydrogen. So it's similar like Hart-Bosch process, but I can do this reaction at ambient pressure and room temperature. And this is actually a model reaction for plasma because it's if you put nitrogen hydrogen, you get only ammonia. So it's quite easy reactions. But the main challenge actually is ammonia yield. It's low ammonia yield and also the high energy cost for ammonia production, compared to Hart-Bosch process. We find actually the one, very important reason actually is ammonia, crack. So very promising strategy we call the shielding protection using porous materials. So for example, we use like the porous silica because we find that ammonia produced, in this kind of process. So there's, the concentration of ammonia inside the pores and outside the pores are different. So ammonia actually can diffuse into the pores. However, we find that the plasma cannot be formed in such small pores because this, the catalytic pores is around like a few nanometers. But plasma can only be formed in the pores with a diameter over 10 micrometers. So in that case, it's probably not a catalyst. So ammonia diffusing the pores and the plasma cannot be formed in the pores. So ammonia in the pores will be protected, will not be decomposed by plasma. So in that case, we can get like over 5% ammonia yield in single pass, at room temperature and ambient pressure. So how we do that? I mean, we actually designed 3 different catalysts, nickel catalysts with different nickel locations just for the comparisons, So one is like a nickel confining the pores, and one is nickel on the surface, and one is nickel in the pores and on the surface. So if you look at the TM, the right ones, and you see the nickel confining the pores has smaller nickel, nanoparticles and distribution. But nickel on the surface has a wider distribution of particles. But in plasma catalysis, I mean, in thermal catalysis, probably the nickel confining pores might work more effectively. But in plasma catalysis, this will be a little different. So first we did we want to understand whether plasma can be formed in the pores or not, because this has not been answered before through experiment. But some people doing some modeling, and they demonstrate plasma can be formed in the pores if the pore diameter is over 10 micrometer. So we did the first experiment is like a TPR, so we can identify 3 different peaks corresponding to the 3 different locations of nickel. Like alpha is nickel on the surface, and the gamma is nickel, in the pores. Then what we did is we first used hydrogen plasma to do reduction of catalyst. So we want to see whether hydrogen plasma can reduce nickel oxide in the pores. Then we do the temperature program, the reduction of hydrogen. We want to see the changes of hydrogen consumption, before and after reduction. Then we can see whether the plasma can be used to reduce, nickel oxide in the pores. Although the hydrogen radicals might be able to diffuse in the pores, but because at low, room temperature, you cannot reduce, nickel oxide to nickel. So we actually can see that these figures actually plasma cannot be, generated in the pores. So this is very important, the findings for this work. If we look at the main results, for example, we also use the control catalyst. So this figure gives you 3 very important information. One is porosity is very important if you compare silica oxide with mesoporous silica. And the nickel is very important because you need nickel to activate nitrogen. And also, accessibility of nickel site is very important. For example, nickel in the pores actually has limited interaction with the plasma because the plasma cannot be formed in the pores. But nickel on the surface has, has much higher, ammonia, the production rate. So if you look at the right one, you see that although nickel silica oxide has more, nickel sites, but actually it has, the poor ammonia synthesis rate compared to the other materials with porous structure. And if we compare, we do the benchmarking with the previous literature reviews, and we can see we can get a very high concentration of ammonia, although the energy yield actually is still low, compared to the, Habosh. I mean, the target should actually go to the right corner, to get about like 100, grams ammonia per kilowatt hour. And we did also 50 hours, so it's quite stable. So we did, the switch on, switch off, cycle test to demonstrate the intermittency of, the process. And also we can change the power input and see it's also quite stable. One significant challenges for plasma catalysis actually is, in situ, catalytic characterization, on the plasma activation, because we normally don't have like this kind of facilities, So we actually build a plasma reactor, which can be fit into FTR. So this is transmission mode actually. Then we can actually understand what kind of intermediate species formed on the plasma surface. So this is quite important to understand the reaction mechanisms rather than just measure the ammonia at the outlet. So this actually recently, I mean, there's few groups also working on this kind of in situ. We have also demonstrated this system for the range of plasma chemical reaction, including the ammonia synthesis, taurine reforming, CO2 hydrogenation, and dry reforming, and also water gas shift reaction. So demonstrated its effectiveness for to address this kind of challenges. So this is one result for the we actually first we introduced nitrogen plasma, and then we can see that one the peak, and when we actually introduce hydrogen, and this peak disappears and also forms NH and NH2. If you look at this the left figure, you can see this MCM, out actually has more, NH, NH2 species, which are, important for the formation of ammonia. So another very important, I think, experiment is we want to demonstrate this kind of, the concept. So we did a desorption experiment. So first one, we switch off plasma, then we do desorption just to purge, the gas. Then we can see the MCM out actually, have retained more ammonia in the pores. So you see the accumulated ammonia, the desorption, amount is highest compared to the other materials. And on the another hand, you see another experiment is we do first one, we compare the silicoxide with MCM41, one without, porous structure, the other one with porous structure. And we do the initial absorption, then we do ammonia cracking, then we do reabsorption. And so you can see for silicoxide, the two absorption actually has similar time. But for the MCM41, you see the second absorption has less time. That's because the structures, the porous structure has already retained ammonia, which has not been decomposed. So the second absorption requires less time to reach the saturation. So this actually, to demonstrate this kind of, the catalyst can be used to actually the ammonia, this actually shift the reaction equilibrium. We actually further actually extended this kind of, shielding protection, the catalyst demonstrated to sorption enhanced. It's like, you sorption, ammonia during the production, and you actually shift, reaction equilibrium. So we can use something like sorption enhanced plasma catalysis for ammonia production. So this actually, the sorption enhanced concept has already been used also in, thermal catalysis. It's like some, the materials, or some people using membranes, also something like this one. So we actually got one, European grant on, sorption enhanced plasma catalysis for green ammonia production. So this is a 3 million European grant, and including 6 partners, led by DTI in Denmark. So it's a 3-year project. The previous, actually, this route still, had the significant challenges in terms of any cost. So there's another very promising route. I previously mentioned is the BE process. So this one has recently also, come back to the community again. Is because this process is more promising and also has a low energy cost. So this is like a plasma-based BE process. But the BE process, in 1903 actually used a thermal plasma, which is high temperatures. But at the moment, we actually mostly use no thermal plasma, which has low temperature for nitrogen activation or nitrogen oxidation. So this process, actually, you see that you can use air. You use a mixture of nitrogen and oxygen, but you can use air. You can produce high concentration NOx. So in the past, we want to remove NOx, which is low concentration NOx. But at the moment, we actually want to produce high concentration NOx, typically a few percent, like 3%, 5%. Okay, and you put into water, you get a nitric acid. So this is one-step process to produce nitric acid compared to thermal process. The thermal process, you need ammonia and ammonia oxidation, right? So this is a very, a one-step process to produce nitric acid. But if you want ammonia, you can easily combine with electric catalysis to, to do the reduction of nitrate and nitrate to ammonia, which is very feasible, compared to electric catalysis for the reduction of nitrogen with water to ammonia. So if you combine these two together, you can also produce ammonium nitrate, which is fertilizer. So this process, actually, you can produce multiple nitrogen compounds, actually, NOx, nitric acid, ammonia or ammonium nitrate. And also the process, actually, the feedstock is cheaper. It's only air and water, and use renewable energy. You can switch on, switch off instantly. And also this process can be used for the agriculture, for example, AD section, anaerobic digestion, because this kind of NOx can be used to actually inject into the digestate from anaerobic digestion. Then you actually can fix ammonia in the digestate to reduce ammonia emissions for farmers, but also you produce fertilizer. So here actually, the one actually important aspect actually again is also energy cost. So it's very important to actually to reduce any cost for the plasma process. Because in the past, in 1903, the cost is like 2.4 megajoule per mole, which is about like 5-6 times of the Haber-Bosch process. Oh. Where's my slide? Okay, so this actually initially, a diagram to show the ammonia concentrations and any costs using plasma, no thermal plasma for NOx production, because this is a very important process. So once actually you can get a very, economic feasible process for nitric acid production, you can also combine with other green ammonia production, to produce ammonium nitrate. So I just, so currently actually, we can get about, it's important to actually get a balanced, NOx production and energy cost. So at the moment, I think we can get like about 3% NOx, but with the lowest, the energy cost, is about 1.1 megajoule per mole. So which actually is about like 2 times of Haber-Bosch process. The Haber-Bosch process is about like 0.506, and the BE, using thermoplasma is about 2.4. But this is it's very important, and because we have typically have very low capex, because we don't need high pressure systems. So this actually the process to produce, for example, like nitric acid is quite promising. It's compatible to the conventional process. So I give a brief summary. So for example, for the ammonia production, from nitrogen hydrogen route, it's very important to actually need to design a catalyst. At the moment, I think for this process, we need some catalyst. We currently also combine with, for example, using zeolite, because zeolite is normally used for the ammonia separation. So we try to combine the ammonia separation with ammonia production in the same reactor. So it's important to consider, like this kind of the concept to actually to remove ammonia, during the production to avoid or limit, reduce ammonia decomposition, which is reverse reactions. And also regional design is very important, because regional design is actually is based on whether you can understand the reaction mechanism. So it's very important to actually develop like in situ, analysis technology for plasma catalysis. So currently it's most we already have like in situ FTR, but also some groups they working on the in situ Raman, in situ even in situ XAS. And also, for the B process actually currently is quite promising, because it does not need any hydrogen. It's just use air. You can produce NOx with high concentration. Then you can produce nitric acid. Then it can you can combine with electric catalysis, which is very feasible to produce ammonia or ammonium nitrate. So this is also quite promising. It's like a tandem process. It's more like the first step using plasma to activate, like inert molecules. Then you combine with second process with like conventional process, like some electrocatalysis or photocatalysis on the ambient conditions. And you can produce like multiple nitrogen, products. You can also do some like carbon nitrogen coupling, for example, using electrocatalysis of CO2 reduction to produce like urine or something. So if you're interested, you can also read our roadmap on plasma catalysis. We also talk about the fundamentals, but also different reactions. CO2, like emitting conversion, and also ammonia synthesis. And we also have a book on plasma catalysis. And these collaborations and also the fundings to support the research. Thank you.
Okay, thank you, Professor Tu. Is there any questions?
Thanks for your great talk. So FTIR, so is your plasma cell embedded affected or no? Is the FTIR system affected by your high voltage plasma?
No, it's the current. This one is transmission mode. So we actually put a plasma reactor into the gas cell. So for example, if you use a drifter, then you have to modify the drifter. You need to redesign the drifter because you need one window with plasma. Well, for this one, it's more like a plasma reactor which can be fitted into a gas cell. Then you put gas cell in the FTR. So we don't have like interference from plasma, like high voltage or something. Yeah.
Okay, thanks.
Yeah.
Thank you, Professor Tu. So very nice talk. I have a small question. So I'm very interested in the first part. You reportedly mesopolar silica confined the nickel for the plasma nitrogen fixation. So according to the conventional thermocatalysis, Jean Noskov, they propose a scanner relation.
Oh,
the nickel shows very weak interaction with the nitrogen molecule. So in the plasma case, I found the activity seems the ruthenium metal is much better than nickel. So what's your opinion about the two differences?
The volcano curve that shifted for plasma catalysis compared to thermocatalysis. I mean, this was published in Nature Catalysis paper, a few years ago by the University of Notre Dame.
Yes.
And the one reason I think is because in the plasma process we have nitrogen excited species, which actually it creates additional reaction route, compared to like thermal process. So this actually shifted, the volcano curves. So the current, I think, for plasma catalysis for ammonia production, nickel, cobalt, they're quite good. It's not like iron. Iron is not good for plasma catalysis. Yeah.
So did you try to perform any relationship between on the plasma condition?
Yeah. They did some like volcano curves and see the shift, compared to like plasma catalysis and thermal catalysis. Yeah.
Okay, that's very interesting. Thank you.
Yeah.
Okay, Professor, very nice talk. So I have a simple question. So compared to the present Haber-Bosch process, the energy efficiency seems to be a little bit low for the plasma assisted process.
Yes.
So do you have any comment about the future improvement for this process?
Yeah, for example, for this ammonia synthesis from nitrogen hydrogen, I mean, currently the energy cost is much higher, probably like 10 times of like Haber-Bosch process. So we really need to enhance, the ammonia production, I mean, the yield, but also at the same time reduce the energy cost. So one actually, this actually design strategy could be very useful to, significantly enhance the ammonia yield, then reduce the cost. But we found that we did some TEA, techno-economic assessment for many of also this process, but also like CO2 hydrogenation. We found that the plasma process can significantly reduce the capital cost. For example, for like this kind of NOx production, and we only have like 50% of the conventional process. So the energy efficiency is not the only, the parameters determine the overall cost, because the energy efficiency affects your operating cost, but you have very low capacity cost, so you can actually make the process more attractive. But for the NOx production, actually, that route is more feasible at the moment, based on the TA, the calculations. Yeah.
Okay. Thank you very much. Okay. We thank Professor Tu again. Our next speaker is an invited speaker by Jianping Guo. He's a professor from Dalian Institute of Chemical Physics, and he has done a lot of work about ammonia synthesis based on hydrides, amides, and imides. And he also has some exploration in the plasma-assisted ammonia synthesis system. So the title of his work is his talk is nitrogen fixation by hydrides on the plasma.
Thank you, Professor Wu. Firstly, I ask to provide me such an opportunity to share our recent work on nitrogen fixation by hydrides under plasma. I'm from Dalian Institute of Chemical Physics. My my presentation includes two parts. The first one, I think Professor Tu Xin has already given us a very comprehensive introduction on the research background of ammonia synthesis. So I think I would like to skip the background part and go straight forward to the challenges of nitrogen fixation. And the second part, I will introduce our part of our recent work on hydrides for chemical looping ammonia synthesis. This part also includes the thermal chemical looping and plasma-driven chemical looping ammonia synthesis. Yeah, let's see this reaction. Ammonia from dinitrogen and dihydrogen. From the thermodynamic point of view, this reaction, in principle, can be operated at room temperature and pressure. You can see here the at room temperature and pressure, the thermodynamic equilibrium ammonia concentration can exceed 90%. But we know in industry, the ammonia synthesis process can only take place at very high temperature and high pressure, even with the presence of active ruthenium and iron catalyst. So you can see there's a very huge gap between the thermodynamic and the kinetic issue for this reaction. So what is the reason for this contradiction? For my understanding, I think there are at least three parts. The first one is the dinitrogen molecule is chemically inert with a very high nitrogen-nitrogen triple bond energy and a high homo-LUMO gap. And also dinitrogen is nonpolar, so it is not a good electron field and nuclear field reagent. The second part is that in the ammonia synthesis reaction, the absorption of dinitrogen and dihydrogen usually competitive. So in some cases, the strong absorption of dihydrogen will inhibit the absorption and the activation of a dinitrogen molecule. The third reason, I think, is the scaling relations, which has been revealed by Professor Noskov and his colleagues. So from the scaling relations, we can see on the transition metal surfaces, the absorption energy of this nitrogen species. For example, hydrogen, and hydrogen 2 species, they scale with each other. So that means that it is very difficult to tune the absorption energies of these species independently. So these scaling relations tell us on the transition surfaces, it is very difficult to get a high dinitrogen dissociation rate and a high hydrogenation rate of nitrogen species. So that is very difficult on transition surfaces. So our basic idea is that if we want to achieve the low temperature and the low pressure ammonia synthesis, we should develop a new dinitrogen fixation mode and reaction pathway. So we are thinking about the transition metal-free catalysts for this reaction. So we are working on these hydride materials. So hydride, you can see the hydride can be viewed a combination of proton and electron. So the hydride can be viewed an electron and hydrogen carrier. So as we know, the reduction of nitrogen to form ammonia just need the input of electron and hydrogen. So on this respect, the hydride has inherent relationship with dinitrogen fixation process. So our finding is that this alkaline and alkaline earth metal hydride can fix dinitrogen under heat, light, or plasma conditions to form the alkaline and alkaline earth metal amides and imides. So in this process, the hydride play a key role. The hydride can undergo the reductive elimination or protonation process to provide electrons for dinitrogen reduction and provide hydrogen to form the nitrogen-hydrogen bond. So this reaction mechanism is very different from the conventional transition metal surfaces. This alkaline and alkaline earth metal amide and imide also dissociate dihydrogen molecule heterolytically to form proton and hydride. The proton combine with the NH and NH2 species to release ammonia, and the hydride combine with the alkali to regenerate the alkali hydride. So you can see by this dinitrogen fixation and hydrogenation steps, we can achieve ammonia synthesis reaction mediated by these hydride materials. So I would like to highlight that the interconversion of alkali hydrides, amides and imides from thermodynamically and kinetically is the key to realize ammonia synthesis. So our group has been devoted to the development of hydride materials for ammonia synthesis during the past 15 years. So we have the hydrides in our group include these transition metal free hydrides and also the alkaline hydride transition metal composite catalysts and the complex hydrides, nitride hydrides. However, because of the time limit, today I just focus on this alkali and alkaline earth metal hydrides for chemical looping ammonia synthesis. So let me show you some experimental results. So from this thermogravimetric and mass spectral results, we can see the lithium hydride is lithium imide, calcium imide, barium imide, and in the meantime, dihydrogen byproduct will be produced. But for the sodium hydride and potassium hydride, unfortunately, they cannot fix dinitrogen under thermal conditions because they don't have thermodynamically stable imide phases. This imide product, for example, lithium imide and barium imide, they can also be hydrogenated upon heating to a certain temperature to release ammonia and regenerate the hydride. But the hydrogenation of calcium imide is very difficult. It requires much higher temperature and high hydrogen pressure. So I just show the hydride can, some of hydride can achieve dinitrogen fixation and hydrogenation to ammonia. So based on these two steps, we can construct a chemical looping ammonia synthesis process. So this process has, because in this process, the dinitrogen and dihydrogen are fed alternately into the reactor. So the absorption, the competitive absorption of dinitrogen and dihydrogen in conventional catalytic process is circumvented. So let's show the experimental results. So you can see the chemical looping ammonia synthesis process of barium hydride is about 20 times higher than that in a catalytic process. So this result shows the potential of chemical looping process for ammonia synthesis. So the next question is, what is the reaction mechanism of nitrogen fixation on this hydride? So with collaboration with Professor Wig from Technical University of Denmark, we calculate the reaction mechanism of nitrogen fixation on barium hydride surface. We found that the creation of hydride vacancy plays an important role. After the formation of hydride vacancy, the unsaturated multiple barium atoms acts as the active site for binding dinitrogen molecule, and then the nearby lattice hydride undergoes reductive elimination to provide electron for dinitrogen reduction, and simultaneously to produce dihydrogen. And also undergo the reductive protonation reaction to form nitrogen-hydrogen bond. So in this process, we also found the dinitrogen activation proceed via this associative pathway that is very different from the transition metal surfaces, in which the dinitrogen usually undergoes the dissociative reaction pathway. So let me just summarize above mentioned results. Under the thermal conditions, the alkali and alkaline earth metal hydrides have shown very different behaviors. For example, the lithium hydride and barium hydride can both fix dinitrogen and hydrogenation to ammonia. But calcium hydride, although it can fix dinitrogen, but the fixed nitrogen atoms is difficult to be hydrogenated to ammonia. For sodium hydride and potassium hydride, unfortunately, they cannot fix dinitrogen because of thermodynamic reasons. But if we look at the thermodynamic analysis of this reaction, this sodium amide reacts with dihydrogen to form sodium hydride and ammonia, we will see this reaction is thermodynamically feasible. And our experimental result also shows that the hydrogenation of sodium amide to release ammonia can take place above 120 degrees C. So you can see the hydrogenation of sodium amide is very easy. It's very easy. So our thinking is that if we can realize nitrogen fixation on sodium hydride to form sodium amide, this loop will be closed. But the problem is that how to achieve this goal. We fortunately found the plasma can help the sodium hydride to fix dinitrogen to form sodium amide. So upon exposure the sodium hydride to nitrogen plasma, FTIR result shows that the nitrogen-hydrogen bond stretch vibration can be clearly seen. So that means in this process, the nitrogen-nitrogen triple bond was cleaved and forms the nitrogen-hydrogen bond. And in the meantime, during this process, we also observed a certain amount of dihydrogen. So as I mentioned, for the dinitrogen fixation on hydride surfaces, the reductive elimination and the reductive protonation may take place. So how to understand the nitrogen fixation process under the nitrogen plasma? We think there are at least two reaction pathways. The first one is that as we know, the dinitrogen can be excited to reactive nitrogen species, such as the electronically excited or vibrationally excited molecules or nitrogen atoms. And these reactive nitrogen atoms can absorb on the surface of sodium hydride to form the sodium amide. In another route, the energetic particles in the nitrogen plasma, they can impact on the surface of sodium hydride to break the sodium hydrogen bond and form the dihydrogen molecule. And then the dinitrogen molecule reacts with the dinitrogen in the gas phase to form ammonia. And then ammonia reacts with the sodium hydride to form sodium amide. So this is our understanding on this process. But anyway, the synergy of nitrogen plasma and sodium hydride is the key to realize the formation of sodium amide. So the sodium amide, you can see, can be hydrogenated to release ammonia above 150 degrees C. So you can see we can achieve the plasma nitrogen fixation and the following thermal hydrogenation to ammonia. So this loop is closed. So beside the sodium hydride, we also found the lithium hydride. So this left figure, and this is potassium hydride. We will see lithium hydride and potassium hydride can also fix dinitrogen to form NH or NH2 species. But for the calcium hydride and barium hydride, they don't fix a significant amount of dinitrogen under plasma conditions. The potassium hydride is also different from the sodium hydride. The main difference is from the formation of hydrogen byproduct. As I mentioned before, under the nitrogen plasma treatment, we will see a considerable amount of hydrogen will be formed over sodium hydride. But for potassium hydride, we did not observe the hydrogen formation under nitrogen plasma. So that means the potassium hydride has a high atomic economy in utilization of the hydride ions for dinitrogen reduction. So based on these results, we can construct a plasma and thermal hybrid chemical looping process. So in the first step, we use the plasma dinitrogen fixation on the surface of alkaline and alkaline earth metal hydride to form amide or imide. And this amide imide can be hydrogenated to release ammonia under thermal conditions. So this is the concept of this plasma thermal hybrid chemical looping process. So the red figure shows compares the chemical looping ammonia synthesis rate with some thermal catalysts. So you can see the plasma assisted process has a higher ammonia synthesis rate than the conventional ruthenium iron or cobalt palladium nitride catalyst. So that shows this chemical looping process have potential for the ammonia synthesis reaction. So let me summarize this result. The alkaline and alkaline earth metal hydrides has very different chemical behaviors under thermal and plasma conditions. Under thermal conditions, only lithium hydride and barium hydride work. But under plasma conditions, lithium hydride, sodium hydride, and potassium, they can work. So I think during the past 100 years of ammonia synthesis studies, most work have been focused on transition metal surfaces. However, our work shows that the alkaline and alkaline earth metal hydride can also function as active site for dinitrogen fixation and conversion. These hydrides have different nitrogen fixation mode because they can proceed this reductive elimination and reductive protonation of hydride reaction pathway. That is very different from the transition metal surfaces. So because the rich composition and structure of hydrides, I think there's a very rich chemistry of nitrogen fixation by this hydride. So last, I would like to thank my group leader, Professor Ping Chen, and also my colleagues and students. Thank you. Thank you for your attention.
Thank you, Professor Guo. Is there any questions? Okay, I'm very curious about in the chemical looping process, the stability. So for catalysis, it only takes place on the surface, but for chemical looping, maybe it goes into the bulk.
Yes.
So during the chemical looping process, is the stability comparable with the catalysis process?
Yeah, for chemical looping processes, I think there are two kinds of studies. For one thing, the sample, we call that a carrier, nitrogen carrier. So this carrier, the back phase, sometimes will change. sometimes they just the surface structure changes. For example, in my work, the formation of nitrogen hydrogen species only occur on the surface, of the sodium hydride. So in principle, this surface chemical looping process should be stable than the back one.
Okay, thank you very much. And I also have another question about the reaction routes. So based on your calculations, you suppose that the mechanism is an associative mechanism. So is it applied for all the hydrides or just only for the specific hydrides, like a barium hydride? Is it applied for all the hydrides or only barium hydride?
In this case, this is a thermochemical process. We just calculate this barium hydride. Actually, we also have studied the photocatalytic ammoniocensis on lithium hydride. On that surface, from theoretical calculations, it seems the associative mechanism also prevail on the lithium hydride surface.
Okay. And the associative maybe works in this system?
But for I think under our reaction conditions, that is low temperature, I think the associative mechanism should prevail. From the theoretical calculations, the dissociative mechanism, the kinetic barrier is very high. So that is seems impossible under low temperatures. Yeah.
Okay, thank you very much.
Thank you.
And also your hydrides seems to be very interesting because for the loading metals, the loading amount is very small, but for hydrides, maybe everywhere is active sites, right?
I think it should be the surface. Of this hydride can work. So I think that is a very important question. For this hydride, the specific surface area usually very small. So another work in my group is to how to prepare nano-sized, nano-structured this hydride, alkaline and alkaline earth metal hydride for dinitrogen fixation. I think if we increase the number of reactive sites, the activity should be enhanced.
Yeah. Okay, I'm very looking forward for that.
Thank you. Thank you.
Is there any more questions?
Thank you for the wonderful talk. I think there's one small question I just wonder. The thing is like when we couple the plasma with catalyst, we know normally the surface particles on the catalyst surface is tiny. So during the plasma working process, there will be a sheath. Actually the plasma will formate a sheath, which means like the electrons will be balanced with the heavy ions electrically. So that means that some part of the particles cannot collide with electrons. So this is a so-called plasma sheath. So my question is like, will this phenomenon will affect on the interactions between the plasma and the catalyst? Is there anything happened in this regard? Thank you.
Sorry. You mean the plasma sheath effect in my I think actually in my case I don't take much attention on this this effect. Actually, as I mentioned before, the interaction between the plasma and the sodium hydride should play a very important role in this process. And I also think the plasma may have some effect on the sodium hydride, and the sodium hydride may also make some effect on the plasma. Yeah, but we have tried to use some techniques for example, OES. But unfortunately, we didn't find much difference between our case and the reference. So, but I think your question is important. Yeah.
Okay, thank you very much.
Thank you.
Thank you, Professor. Go again. Our next speaker is Xinhua Zhang.